Let's talk about type conversions. There's actually two types. One is the implicit type, and the other one is the explicit. So what this means is, let's say if we have an expression that involves, let's just say this is a binary, right? That involves maybe even an assignment, or when you have two different types at A plus B, and these are two different data types, okay? So when we say type, we're talking about data type, right? When you do, let's say, add a char, right, to an integer, so both are of different size, right? You can do a size swap to see it. Like, what would be the outcome? Like, what would be the type of the outcome? So that's one thing about implicit type, because you're not really forcing the data type of each of these operands, right? Remember, these are operands. Plus is a operator, right? Since you're not forcing the type, the conversion of a type on the operand side, this is what we call implicit type conversions in C++, in C, in Java, in Python, right? So these all the same rules exist. Now, there's also explicit type conversion that involves casting, right? This is, for example, let's say you put parentheses integer and you said C, right? So what is C? C is a char, right? Maybe C equals, I don't know, A or something to that effect. And you're trying to convert, right, this thing into an integer. Now, this is not type safe. We'll talk about that later on. In C++, they actually allows for a type safe conversion of casting. But in C, we're just just talking about, having parentheses with data type in it to force a conversion. So in the following couple of slides, we're going to talk about various different types of conversion, starting with the explicit type first. Well, this is a conversion rank table. You can think of this vertical as in, right, the size of these, right? Size of, right, each of these types. So we have Boolean, which is 1 byte, right? Remember, this is less than or equal to, right? Which is 1 byte for char. Char is 1 byte. Integer is 4 bytes. So we have 4 bytes here. And real, this is long doubles, right? This is at least, right, 8 bytes. Sometimes it depends on the platform. Long double can be in the range of 12 to 14, 16 bytes, right? Doesn't really matter. As you can see, all of these, right, they're going up in size, right? So if you think about this, right, let's say if we have a Boolean, right? When you say a Boolean, BOL, and try to do an equal sign here, let's do a assignment operator, assignment right here. Let's say on the right side, you have a char, right? A Boolean. So they're roughly equal, so you're not going to get any issue there, right? However, if you have for example, Boolean right here, and then equals integer, right? So integer is 4 bytes, right? As you can see, like 4 bytes, a lot of ones and zeros, right? So there's actually, this is actually 2 to the 32, right? Because there are 32 bits, right? So we talked about this, right? Integer is 4 bytes, which is 32 bits, because each byte is 8 bit. So there's a total of 32, right? 8 times 4. Actually, no. In this case, it's 2, right, to the 8th, right? And each byte, there's actually 4 bytes here. So 2 to the 32. Now that's 32 ones and zeros, right? Line up here. And you try to fit this structure into 1 byte. So what is 1 byte? 1 byte is 2 to the 8th. So there's only 8 slots, right? This is not drawn to scale, by the way. So Boolean has 8 slots, and integer has 32 slots, right? So when you do an equal sign, right? So you're forcing a very big item, right, into a very small box, right? Then what happens is you lose positions, right? So immediately your entire right-hand side is demoted, right? Demoted into this Boolean data type. So this is what we call demotion. So when this happens, you don't really have to memorize this. And on the other hand, the opposite of demotion is what we call promotion, right? Let me give you an example and then see, you can visualize this if you will. So let's say if you have a flow, okay, and flow data type, right? And then you say flow, this flow equals integer, right? So as you know, integer has 2 to the 32, right? So there's 32 slots here. And flow, right, is much, much bigger, right? This is of 8 bytes. So there's actually 64 slots. There's 64 slots here. There's 32. So of course you can fit, right, the size of an integer into flow. There's actually still plenty of, right, empty slots left, right? This empty slot indicated by this shaded area. So this is what we call promotion. You're promoting this entire integer, which is 4 byte, into an 8 byte. This is what we call promotion. Okay. So I don't want you to think too much about, promotion, demotion, because it's hard to memorize this kind of stuff, right? But what I want you to do is to visualize this entire thing, right? Float is big, right? And then you have a small item, right? It's putting a small apple into an entire basket, right, of apples. That way, you get a lot of empty zeros because, there's lots of paddings with nothing in it, right? So you only filled up half of the basket. This is what we call promotion. And on the other hand, when you try to shuffle something that's big into a small basket, that item is so big, you can only shuffle maybe shove 50% of it into it, and the other 50% is gone, right? So you lose precision. That's what we call demotion. Generally, promotion is better because you maintain, right? You keep track of your accuracy. Demotion is bad because you lose precision. So in scientific calculations, when you have a demotion, you definitely lose value, and your end results, like your entire algebraic expression, once evaluated, will not be as accurate, right? So that said, this is what we call the conversion rank, right? When we're dealing with implicit. So there's also other types of implicit conversion. Let's look at the other type that involves not just assignment operators, but let's just say, we have a complex expression a plus b, right, equals something, equals c. Like, what is the type of c, right? This is another type of implicit conversion that we will talk about and look at in the following slides. This is a quick program here. Just remember, b is Boolean, c is char, d is flow, I is integer, s, right? Whatever their values are. Let's look at what we're doing here. So you have an addition algebraic expression saying c equals c, right? C is char, right? So char is 1 byte, Boolean is 1 byte. So if you add them up, at some point you get a char. Boolean is promoted char, right? So you get a char, right? Why? Because char is 1 byte, and 1 byte plus 1 byte, it's not 2 bytes though, right? This simply just means that you're adding the value of 1 byte, right? This 1 byte could be 1, and the other one could be 3. I say this is 1, this is 3. So you're getting a 4. But the resulting is a char, right? Because you take the bigger one. So this is an example of where b Boolean promoting to a char, right? So if you think of like Boolean is actually less than or equal to the size of char. That's in this case. All right, let's look at the very next one. The next one is these digit flow. Flow plus a char, right? So flow is a pretty big, right? 8 bytes. Char is 1 byte. So when you try to shuffle a small apple into a huge basket, right? You end up getting that basket itself, right? Because that small blimp in the sky and the horizon, namely this C, doesn't really add to the weight of your end result. So you can really think of it as C is getting promoted, right, to a flow. So in effect, let's just see C is only 1 byte, just the entire C. When it promotes to a flow, right, you end up having this entire structure. This is all zeros, right? Basically all zero, empty, right? The actual stuff is here, right? So in this case, C gets promoted to flow, and now flow plus flow equals float. B is a Boolean, false, so there's nothing there. But what is D? Minus D is a flow, right? But B is a Boolean. So this is the problem when you have a huge data. This is 8 bytes, even though this is in a negative directions, minus D. It's 8 bytes, right? And then you try to shuffle this giant item, right, 8 bytes into this 1 byte structure, you lose precisions. So flow has to be demoted into a Boolean. By that, what happens is, let's say flow originally occupies this much, right? And by demoting, demoting means try to shuffle this into a 1 byte data structure, this 1 byte right here. So that's what happens. Flow, when demoted into a Boolean, only gets this much, right? And the rest of it is all gone, okay? This is all gone, okay? So flow becomes a Boolean, and this is how you, right, assign a Boolean equals Boolean. So this is an example of implicit type conversion. This implicit type conversion happens first, right? Before this equal sign, right? So that way you have apple to apple, right? Assignment. Again, you can play around with this. This could be done in C++ as well by replacing printf with cout. Okay, same idea. This is another example of implicit conversion. This time we're not doing addition, but we're using assignment, and we're using multiplications, divisions, and stuff like that. Let's take a look at this, right? So when you have a flow, f is flow, integer is I, right? When flow is assigned into a integer, right? This is 8 bytes, this is 4 bytes. You lose precision, right? Which means this flow, what happens to a flow? Flow gets demoted, right? Demoted into an integer, right? So whatever is happening, let's say this flow is 2.5. When it gets demoted, you might get just 2. This thing's assigned into a value of I, right? So I equals 2 after this. Now, you can do this in your console to verify that. Now, we know I is not 2, right? Now, 3 divided by I, right? So 3, what is 3? Now, if 3, if you put a dot after the 3, this becomes a flow, right? If you do 3.0, this becomes a flow, right? Flow double, right? Doesn't matter. Now, since we don't have this, right? I don't have a dot here. This 3 is simply an integer. So what we have here is integer divided by integer, right? Because I is an integer, right? We're talking about this. So this is good. Now flow, right, equals, right, this thing. So what you have here is the result of this is actually integer. Okay. There's no flow here, right? Even though you're doing, 3 divided by 2, the result is 1.2. But what happens is flow will equal 1 after this. Why? Because you have integer, right? And this integer is 1.5. But because the result is actually 1.5, right? But because the entire thing is an integer, right? You can only take, right, what's in front. This 1.5, which is the flow, cannot fit. So you're trying to fit 1.5 is a flow, right, into this small area. So this implicit conversion happens. Is what we call demotion, right? This entire flow, 1.5, right, gets demoted into an integer, which truncates 0.5, getting you only 1, right? But because this entire thing, which is an integer, which is 1, now has to be assigned into a flow, right? So this is a small apple into a big basket, right? What do you get? You get 1.0, right? Why? Because you're only taking 1 from the right side, right? The right-hand side is 1. And you're trying to assign this 1 into a flow, right? Float is 1.0. So that's what happens. This is the reason why you have f equals 1.0 after this. So you can move on, and try to extrapolate using the same idea, using this explicit conversion of integer and flow data to see for yourself. I highly recommend that you go through this whole exercise and try to, various different types of conversions and try to use different numbers to play around until you get what's going on. Now that we spend much time on implicit casting, let's talk about explicit cast, right? So explicit cast happens on a unary expression, right? So let's say if you have a, right? A is, right, integer, let's say 2. The way that you would explicit cast to a explicit casting of a is by writing a parentheses. Let's say you want to convert it into a double, right? So this is explicit casting. Okay, so instead of allowing, right, your compiler to do the conversion yourself for you by demoting it or promoting the operand, now you're explicitly telling, right, your compiler that you want to cast, right, or convert, right, this integer into a higher level, a double data type. So we can do that pretty much across. Let's move on to the next one. So you can see that here you are seeing that the explicit casting of various different arithmetics and algebraic expressions. Integer number 1 divided by 2, and you try to cast the entire thing into a double. So this entire thing becomes a double. So this is a double. You can also do this, right? and try to print them out. So I'm not going to spend too much time into it. As you can see here, float number divided by float number, this gives you, right, this entire expression gives you a float, right? And if you try to cap, so float is 8 bytes, right? 4 to 8 bytes. Now, if you try to typecast everything into 1 byte, right, char is 1 byte, you're going to lose a lot of precisions. And that's exactly what you're going to see here. This is an operation that sometimes developer wants to, constrain a type box, right? Constrain a much bigger data type into a small one. And sometimes the developer may want to, expand, right, what you have from an integer into a flow, so you can use it for scientific calculations and whatnot. So there's various different reasons developers do this. Sometimes you may be getting this information coming back from a response object in a web transaction, for example, and you want that entire, information to be of type double, right? Maybe that's what your caller function is expecting. So in that case, you do a double conversion that way. So these will have to be done through this explicit typecasting. Now, in C++, there's also a safer way of do an explicit casting, right? To maintain the integrity of the pointer or the type that you're trying to cast it into, to ensure that you don't just convert orange into an apple. You can't do that, okay? In order for this to happen, right? For example, this cannot be a string, right? So if this is a char or a string, and you're trying to convert it, into a double, you're going to get into some error. So in C++, there's type safety constraint as well. Is part of some of the macros at runtime, but C doesn't have that. Actually, I think C has it, but this is not an example that illustrates it.